In this video, I want to discuss how we can use u-substitution to solve a definite integral. So suppose we're trying to find the area under some function, like, I don't know, it's like x minus 2 cubed. There we go. That's some function, but we want to find the area from some definite bounds on this, right? So let's say it's going to go from 3 to 4. There we go. That's some function. We want to find the area under it. But we want to use u-substitution. So we can use u-substitution to help us figure out what the antiderivative is, right? U-substitution can tell us the antiderivative. U-substitution can say we can find the antiderivative of this by changing it into the language of u's. So let me make u the function inside the other function. I'll make it this x minus 2 piece, this x minus 2 piece. So then I'm going to have my derivative of u, my du, is just 1. So du is just dx, right? Du dx is 1. You bring the dx over. So du is just equal to dx. That 1 doesn't do anything. The derivative of x is just 1. Which means here, when I translate this into language of u's, I have just the antiderivative of u cubed du. And I can solve that to get u to the fourth with a 1/4 out front. We're using the power rule for antiderivatives. The 3 goes up to 4, but then you need a 1/4 out front, plus, plus a constant. But I don't actually care about this plus c, though, because now that I have the antiderivative, well, there are two ways I could solve this. One way is I could change this back to the language of x's and say that's just 1/4 x minus 2 to the fourth. And there's a plus c, but I don't actually care about that plus c, because if this is my antiderivative f of x, remember we solved this problem by just finding what is big F of the upper number 4 minus big F of the lower number 3. And so I'm just going to plug 4 and 3 into this. And since I'm going to be subtracting, if I had done a plus c, I would be minusing the plus c, and so that would get canceled. So I don't really worry about the plus c when doing the definite integral. I need it for the indefinite, but I don't need to keep track of plus c for the definite integral. So what do I get? Well, I plug 4 into this, and I get 4 minus 2 is 2, so it's 1/4 of 2 to the fourth power, minus, plug in 3, 3 minus 2 is 1, so minus 1/4, 1 to the fourth power. And then I could simplify this down, and what do I get? So let's see, 2 times 2 is 4, that cancels with this, leaving me with another 2 times 2, so that's 4 minus a fourth. 4 is 16/4, so 16 minus 1 is 15/4. There you go, 15/4. And that's how we solve it with u-substitution. So all we do is we did the u-substitution in order to figure out what the antiderivative was, and then we solve it like typical using the fundamental theorem of calculus, to find the definite integral by plugging in the bounds into this function. But while this is a perfectly good way to solve it, there's another approach we could have done instead. And so let me show you this alternative approach that saves you a little bit of time, but really comes out to be the same thing. This is a good way to do it. Here's another way you could do it. I'm going to keep track of the fact that this bound is 3 and 4. But then what I'm going to do here is I'm going to say when I change from x to u, I'm going to keep track of how these bounds changed. So here I had x is 3 and x is 4. But if x is 3, what is u? When x is 3, my u is x minus 2, so my u is 1. And when x is 4, my u is 2. And then what I'm going to do is when I convert this, when I solve this for the antiderivative of u's, I'm going to just plug in these u bounds. This u equals 1 and this u equals 2. I don't need the c because I'm going to subtract, so the c would cancel. So what do I get here? I plug in the 2, I plug in the 1, I get 1/4 of u, so that's 2, of 2 to the fourth power, minus 1/4 of u, that's 1 now, to the fourth power. And that's exactly what I had before. Just like before, this will come out to be 15/4. So what's the only difference here? Well, the first time I did this process, I found the antiderivative with u, I changed it back to x, and then I plugged in. The second time I found the antiderivative, I left it in u, but I changed the bounds. I plugged in new u bounds into it to get the answer. So you can either convert the antiderivative back to x and use the x bounds, or you can leave the antiderivative in the language of u, but then you have to use the u bounds. Okay, let's look at one more example to make sure we have the hang of this. Suppose I want to solve what is the definite integral from 1 to e of ln of x divided by x dx. Okay, there's kind of a wild graph. You can kind of try to imagine what that graph looks like. You can graph it and calculate it if you want to, and look at that area from 1 to e. We want to find what is that area? What is that area? And so this is not something I can just look at and know what the antiderivative is. So I want to use u-substitution. So I can look at my u-substitution. And so u-substitution, what do I make the u? I don't know. Like, do I make it the x? Well, if I make u x, this is just going to become u, ln of u, du. Nothing changes. I just change all my x's to u's. Whenever you make u equal to x, you don't actually change the problem at all. So that's not going to be a helpful substitution. So I guess the only other thing to try is u equals ln of x. I know we say u is typically the inside function. Maybe it's not obvious how ln of x is an inside function, but it works out here. Because if we make u equal ln of x, then notice what you have. The derivative of u, your du dx, is 1 over x. And so your du is just 1 over x dx. I move the dx to the other side. And here I have a 1 over x, right? Dividing by x, that's the same thing as having ln of x times 1 over x dx. So I have this. I have this 1 over x dx that I can replace with du. And I have this ln of x that I can replace with u. So u-substitution allows me to change this into a u and a du. It's just the antiderivative of u du. Okay, how about your bounds? Two options. We can leave everything with these x bounds, and then at the end, change the answer back into x's. But what I'm going to prefer to do is I'm going to change these x bounds to u bounds. Right? Originally, these were bounds for x, but we can figure out what are the new bounds for u. If x is 1, what is u? Well, ln of 1 is e to what power is 1? 0. So this bound and bottom becomes 0. And ln of e to what power is e? Well, that's just 1. So this is just 1. So my bounds 1 and e become the bounds 0 and 1. And now that I've changed it to u bounds, I can just solve this problem, keeping everything with u's. I don't have to go back to the language of x's. So here we go. The antiderivative of u is 1/2 u squared. And I'm going to plug in my u bounds. I'm going to plug in 0 and 1. And I just keep rewriting u equals to stress that I've changed these from x bounds to u bounds. What you don't want to do is you don't want to plug in these x numbers into your u equation. So I'm trying to stress that I've changed these into u bounds. Because now I just plug in the top one, 1/2 1 squared, minus plug in the bottom one, 1/2 0 squared, and it just comes out to be 1/2. So nice answer. But notice the trick here is I change my problem into a u problem, I solve it, but then I just plug in the bound because I've changed the bounds to u bounds. Alternatively, instead of doing this, what I could have done instead is I could have changed this back into x. I could have made this back into ln of x. But then I would have to plug in not the u bounds, but the original x bounds. X goes from 1 to e. Of course, when you do that, you get the exact same thing. Because what is ln of x? What is ln of e? Well, ln of e is just 1. So this just becomes 1/2 of 1. I'm sorry, this should be ln of x squared. It was u squared. So that's just 1/2 of 1 squared minus, and what is ln of 1? Well, that's just 0, so that's just 1/2 of 0 squared. Plugging these in here is exactly the conversion we did up above. So it's the exact same answer You can just pick that. The only thing to keep in mind is when you're plugging in, make sure you're plugging in the right thing. If it's plugging into the equation of u, you want to convert the bounds to u bounds. If you're plugging into an equation with x, you want to leave these x bounds the same as they were originally. You can decide which process you prefer.